Another topic I wanted to comment on is Doppler-free spectroscopy solution number 3, the saturation spectroscopy setups. I'm doing this because from previous exams I've learned that there's sometimes a bit of a confusion. So let's cover this. It's just like 5 to 10 minutes, and that's all that you need to know about saturation spectroscopy. We start with this differential equation for the adsorption. So the amount which is adsorbed is proportional to the incoming intensity, but also to the piece of matter that we have traveled through. So with this setup for the dependence of I, we obtain the solution that the intensity has an exponential decay where we have some adsorption coefficient in the exponent times the thickness. So that's the usual situation for any type of matter. The more you have, the less intensity you will have in transmission, because more and more gets adsorbed and the dependence is exponentially in the thickness. Now I just realize I'm sorry, but here in the slides, in the PDF conversion, something must have happened, I guess. So number of adsorbers is obviously Ni, and the attenuation cross-section is this sigma Ik. Things are getting interesting now if we have rather high intensities. Why? Because this number of adsorbers, Ni, will be dependent or is dependent on the incoming intensity, because if you excite the molecule, then this ground state or initial state is no longer available, which means that you lose number of adsorbers, and therefore your absorption will go down with increasing intensity, which is seen here in this differential equation for this more detailed description of the actual situation. We have di, the change in intensity, dependent on the incoming intensity, times the cross-section. And here now we have Ni, which is changing because we have Ni minus Nk as a function of the intensity. So Nk is the number of excited states at a given, or occupied excited states at a given intensity. So you can see, or you can assume, that with increasing intensity, more and more of the molecules originally in their ground state will be excited, and therefore they are no longer accessible for another excitation, and therefore your overall loss of intensity will be less with incoming intensity. In other words, this absorption coefficient alpha is a function of the actual intensity, and therefore we speak here of nonlinear optics, and we will take advantage of this effect in spectroscopy through the saturation spectroscopy setup, which I'm going to discuss now on the next slide. So let's assume you just have one laser, but your laser can be adjusted, so you can go through different energies. So you scan over the wavelength and you look at the transmission. So meaning you take your laser, you make it shine on a probe, on some sample material, and you look at the transmitted intensity as a function of the frequency. Now what you obtain is this. So at first it's just a curve that goes down in the region where you are in resonance, meaning that you are exciting some transition in this molecule. So in this moment, your transmission goes down. Now, be aware that this is very broad because we have this Doppler problem here. Let's assume that we are doing some spectroscopy on molecules in gas phase, or even in a plasma or whatever. So we have a very high temperature, we have this Doppler effect, and therefore this is very broad here. Now, if we take a second laser and shine light of a specific frequency onto our sample, say this is in this energy range here, and then scan again, we will get the same profile as before, but at the position of this other laser, we will get a small peak here in our transmission, meaning that in this region we have slightly more transmission than before. Why? Because the second laser that came in at this constant frequency, so with this fixed energy, creates a hole for us basically, because this laser is already exciting the molecules with this energy. And therefore, when the other laser scanning through is in this regime or at this energy range, we will have more transmission than before, because the molecules are already excited and the photons we provide with the scanning laser are going through, at least for this energy range where the other laser is exciting. So in short, we create a dip in the transmitted intensity, or we can also think of the population of the ground state, which is reduced for some energy due to the other laser at fixed frequency. Okay, so this is just a thought experiment, right? We have one laser that can scan and the other one is put at a fixed frequency. But this is not our final setup for saturation spectroscopy. Our final setup looks like this. We have our tunable laser here, and we create a second laser basically through splitting of the original beam. Okay, so this is our beam splitter. It splits it into one beam that goes through a mirror and then through our adsorption cell. This should be absorption cell actually, to give it a better meaning. And the other beam goes through the splitter to a mirror and comes in from the opposite side. Now we call the first the probe laser and the second the pump laser. We know that they are both coming from the same laser, meaning that when we tune now through the wavelength, so we change the frequency or the energy of the photons, this is done in the pump as well as in the probe laser. And we go through the range of the spectrum where we assume to have our resonance, which is at the moment sort of buried under the Doppler broadening. A quick note before we go to the next slide: this angle here is just for illustration, so meaning that the probe and the pump laser are anti-parallel, so this angle can be considered 0. How does our transmission as a function of the wavelength now look like? So this is our transmission signal here, and if we scan over the frequency regime, we see again this loss of transmission signal in the region of this Doppler broadened resonance of our molecule. And fortunately, in this new setup with the laser and the other laser coming in anti-parallel, we have a little peak here, and this peak is sitting exactly at the unperturbed resonance of the molecule. So this is what we want. Why is this peak now here? Think of it this way: we are having a laser coming in from left and one coming in from the right. Now, if a molecule is moving because of its temperature, it moves either towards one or the other. If it moves towards the left, it moves away from the right. So the Doppler effect will be always opposite for the two lasers. This is a good thing because there is only one velocity group of these molecules for which both lasers will feel the presence of each other. And this is only which velocity group? It's the group of molecules which velocity v equals 0. So for all those molecules which do not have a velocity component in the direction of the lasers, there will be no Doppler effect. And furthermore, for this group of molecules, the two lasers are feeling each other in the sense that the pump laser has already excited the initial state to some excited state K. and therefore the probe laser goes through with higher transmission probability because it does not get absorbed that often anymore due to this saturation effect. We can now further improve the signal to noise ratio in this experiment by doing the following. We can also start to chop the pump beam. The pump laser is modulated, for example, through you think of a fan that periodically cuts or chops into the laser beam. And we now look at the signal of our transmission of the probe beam as a function of this modulation, because only if the pump laser is on, this effect should occur and we will see this extra peak coming up. So if I just compare the two signals with the pump beam on and the pump beam off, I can get a better signal because what I'm doing is basically just taking the time derivative and looking at this signal as a function of the frequency of the two lasers, and then I get this nice signal here sitting exactly at the unperturbed resonance of the molecule we are looking at. So we're going back quickly to the previous slide. Here we can see this chopper that cuts the pump laser, and the signal goes in a lock-in amplifier which is connected to our detector, which allows us to compare the signal with the pump laser on and off to get this time derivative and an improved signal to noise ratio. This slide gives now an example of saturation spectroscopy and sort of links our lecture here with previous lectures of Professor Koch or Professor Sterrer. So this is about the fine structure of the hydrogen atom. So we're looking at the Balmer line H alpha, and just for you to remember, back then we started solving the Schrödinger equation for this system of having a single electron in the field of a proton. So we started with the Schrödinger equation, solved it for this problem, and ended up with energy states which are only depending on the main or the principal quantum number n. Then you have to improve on this, doing corrections, introduce spin-orbit coupling and other relativistic effects. So you go to the theory as described by Dirac, and we see that energy levels are still, they split with respect to J, with J being the total angular momentum quantum number of the electron hull. So we have J equal 3/2, where L is 1 and S is 1/2, or the situation J equals 1/2, where L is 0 and S is 1/2, or L is 1 and S is minus 1/2, both giving us J equal 1/2 in combination. And in the Dirac theory, there is no difference in energy between these two substates that form the J equal 1/2 state. But if we go to quantum electrodynamics and introduce a quantization also of the electromagnetic field, we will end up with the Lamb shift, which removes this degeneracy for same levels of J. So we have this splitting, which is very small. And in order to see the splitting, you have to be in your resolution good enough. So Doppler broadening has to be fully removed. And this is done here with saturation spectroscopy. And you can see the comparison on the right-hand side. So here, the upper right figure just shows these energy levels with the corresponding nomenclature that we introduced for atomic excitations. I'm just repeating this quickly for you. For example, let's pick this date. It's a 2p1/2, telling us the principal quantum number n is 2, angular momentum is 1, so L is 1, giving us a p state, and the total angular momentum of the electron hull is giving us the sum of L and S. So L is 1 here, and S must be minus 1/2, so J is 1/2, and we end up with the 2p1/2 state. Now theory tells us that we have to expect 7 transitions. 2 of them should be, though, very low in intensity. And we compare the spectrum without Doppler reduction to the spectrum we obtain with saturation spectroscopy. So we can see the lamp shift between these two peaks, this peak here and here, because the splitting here in this upper level, 3p 3/2 and 3d 3/2, is negligible. So it's basically this energy splitting that we see in the spectrum, the difference between the 2p 1/2 and the 2s 1/2 here. Note that there is also the phenomenon of crossover resonances, giving us this peak here, which is just accidentally sitting at this transition that we see here, but that transition here shouldn't have much intensity at all. So this is a feature that comes in from our technique. So it is an artifact of our saturation spectroscopy principle, which stems from the fact that two unperturbed resonances of this molecule or atom can be coupled accidentally via molecules of just the right velocity. Just imagine a situation where you have photon energy which is perfect for exciting the molecule from A to B. For molecules with velocity v equals 0, but then you also have molecules that move, for example, away from one laser. So for them, the energy of the photon will be lower and therefore not in resonance. But it might be that there is another intrinsic resonance of this molecule, which is simply at lower energy, which might fit now to be coupled. So if the velocity is right for bridging this energy gap between these two intrinsic excitations of the molecule, you can see this resonance peak in the spectrum. However, note that these crossover resonances are determined by the actual positions of the transitions in this molecule, and if you know a little bit about these positions and the actual spectrum, they are very easily identified and distinguishable from the actual transitions.